Derivative of y equals x squared from first principle. Classical method, or using the formula. With the classical method, I have sketched the curve of y equals x squared from x greater than 0 or equal to 0. So from there, x above. So that's what it's a parabola. So it goes like that. But I'm only looking at this side. So we're going to pick a gradient. We're going to find a gradient of this curve. So that's what we're doing using classical method. So if I pick these 2 points there, and that point here is x, and that meant this is y. So the coordinate here will be x, y. And if I pick that point there and bring it down there, that will be x plus delta x. So that will be coordinate here will be x plus delta x, comma, and this is y. So that would be y plus delta y. And so that would be y plus delta y. So that's the coordinate. But the gradient will be this height over that length. So that's the gradient. And that height is called delta y, as you can see, because that's the difference between that and that is delta y. And this length is called delta x. Delta x, which means small change. Now, the gradient on a curve is basically changing from every point on the curve. So the gradients are not the same. So it's very difficult to find a gradient from picking 2 points like that if it's a curve. You can do that for a straight line, but not for a curve. And that's why we're trying to keep the difference here, delta x, very small. That's why we're making it really small, infinitesimally small. And the reason for that is because when you find a gradient on a curve, so if that was a curve like that, you want it to be a point on that particular point. And on that point, you then have a tangent to that point, so like a really nice tangent there, and then you can find the gradient. So basically, because every point along there has different gradient, it's a variable gradient. That's why we want that distance here. So it's as if we're finding a gradient from there to there, the height, and so that we want it really small, so that if you zoom into that, if you zoom into that point, this is what you will get. A perfect straight line. And this little bit will be delta x, and that will be delta y. So if you zoom in there, you zoom, this is what you will get. And that's what we want, because, as I said, the gradient on a curve changes, it varies from point to point, so it's never the same. So this cannot be correct. You have to bring this point down to this point there and to make it like a straight line. And that's what we're doing. So f of x, in this case now, to work on a classical approach, we know that y is also called f of x, which is x squared. And that's for this point here. This point is x, so that's y and x, right? Y and x. But for that point, it's going to be, well, y plus delta y, which we can write as f of x plus delta x. That's what it is, because that's the y. Instead of y, we have y plus delta y for that point. So that would be equal to x plus delta x all squared. So that's what it is. Expand this bit here. We want to expand that. So the expansion of that is going to be x squared plus 2x delta x plus delta x squared. So that's the expansion of that. So that's equal to y plus delta y. So that's what that is. That equals to that. Or you might say, let me put it this way. Y plus delta y equals x squared plus 2x delta x plus delta x squared. Now, y is x squared. Can you see y equals x squared? It's in opposite side. Or take away y from both sides, or take away x squared from both sides. We then get delta y equals 2x delta x plus delta x all squared. By the way, that's all squared. And the reason for that, because y, we cancel that one because it's the same thing. Or if I take y to the other side, minus on y is x squared, they'll cancel that. And so now we're there almost. We now need to divide both sides by delta x, because that's where we're going, delta x. We want delta y over delta x, right? That's what we want. This is our journey. That's where we're going. And then we have to divide that too by delta x, divide that by delta x. Well, delta x over, so delta x, we cancel each other here, and that we cancel one of those, so one left. Delta y over delta x equals 2x plus delta x. Remember, it has to come to that point, so delta x has to be getting smaller and smaller and smaller until it gets towards 0. So we have to say in the limit, delta x has to tend to 0, which implies that delta y over delta x would tend to dy over dx, because then it would be more like that, like a tangent. It'd be more, this is now proper dy over dx. dy over dx, so I'll say therefore dy over dx will be equal to 2x plus 0, because delta x is now 0. So that's how we get the derivative from first principle of y equals x squared. And this is y here. You can see that's y there. So now that looks more like a gradient, where you can then take 2 points on that line here and find dy over dx. Now you can do dy over dx. So now you have the authority to do dy over dx. But before then, before in the limit, we couldn't say dy over dx. So never say dy over dx here, along here. You have to say it after the limit. When you bring that so small, and then that's when you do dy dx. So that's perfect. Now for the formula method, f of x is equal to y equals to x squared. Now f dash x is the gradient, and we write limit where delta x tend to 0, and then we write f of x plus delta x, take away f of x over delta x. So that's one way of writing that. You might say it's also equal to f dash x equals to limit h tend to 0, where f of x plus h minus f of x over h. So you can use either, it's the same thing. So what's going on here? H is basically delta x. Some people just prefer to call it h. Some textbooks are now beginning to call it h. Some exam board are using that as well. So delta x, the classical method, they're now calling that h. So that's the same thing, to just call it h. So this is now being called h. but it's the same thing. So you could use whatever you like. So I could have called this h squared. So that'd be x squared plus 2xh plus h squared. And that's what we're going to do here. So now let's do let's calculate this. I'll use that h here just to show you what's going on. So f dash x equals f of x plus h minus f of x over h, where f of x plus h equals x plus h squared, which will be, so if I expand that, because I need to expand this one, so that would be x squared plus 2xh plus h squared. So that's the expansion. So I'm going to put that here. But you have to say in the limit where h tends to 0. So you must say that. Always when you use that method, you have to say limit h tends to 0. And that will be x plus h squared minus x squared over h. Again, limit h tends to 0. So now we know what x plus h squared is. So that'll be x squared plus 2x h plus h squared minus x squared over h. As you can see, that cancels out, and that will be limit again h tends to 0, 2x h plus h squared over h. H is a common factor here. H is common, so if you take h out here, take h out, it will cancel the denominator here. Limit h tends to 0, 2x plus h, open bracket, h over h. That's h at the bottom there. So I took h out there and h there, so that cancels out. And then carry on by saying f of dash x equals limit h tends to 0, 2x plus h. As h tends to 0, that means h will be 0 here. So I'm going to have just 2x for the f dash x. And you know f dash x is dy dx. So basically dy dx is f dash x, which equals 2x. So that's this formula method that you could use. It doesn't matter, it's just h, or you might call it delta x. And either way, you're doing well. So that's the derivative of y equals x squared. But if you notice, we always do expansion. There's binomial expansion going on every time in derivative. And that will lead to the derivation of the derivative from first principle, and that's what we will do soon.